Good morning, ladies and gentlemen. Welcome to the video notes for Chapter 5, Lesson 1 in your geometry textbook covering bisectors and triangles. Chapter 5 is kind of a unique chapter in that it is actually several smaller micro-units put together of things that are properties of triangles, and they're all fairly important things when it comes to advanced mathematics. They're all things that are very useful, very interesting in geometry. The first two sections of the chapter deal with specific types of line segments that exist within triangles, no matter what size or shape they are, and the properties that go along with those line segments. So section 1 deals with bisectors. Now in a triangle there are two types of bisectors, and that has to do with there being two different types of parts of a triangle. We have angles, which have angle bisectors, which clearly are going to be bisecting the angles. And then we have sides, which have perpendicular bisectors. In other words, perpendicular bisectors are going to be bisecting the sides of our triangle. This first video will deal with the perpendicular bisector side of the lesson. The second video will introduce a related vocabulary term and how it relates to perpendicular bisectors. And then the third video and final video of this section will look at angle bisectors as well as their properties. So, first off, we should remember that the word bisector is not a new word for us. It is one that already exists in our vocabulary this year. We've used it multiple times over the course of the first few chapters. Bisect means cut into two equal pieces. So in terms of a line segment, a bisector is a segment, line, or plane that intersects a line segment at its midpoint. If we look at this picture here, we have markings indicating that AP is congruent to PB, and what that tells us is that P is the midpoint of AB. That allows us to state that PQ is a bisector of AB because PQ is cutting AB into two congruent parts. Now, perpendicular bisector, well, that's a little bit more specific of a term. So a perpendicular bisector is a line or line segment, does not include planes, which intersect a line segment at its midpoint, hence the bisector part. If it intersects at the midpoint, it is bisecting that line segment, and is, get this, perpendicular to the segment. Okay, so it has two things that have to be true about it. One, we have to see boxy. We have to see some sort of indication that line RS is perpendicular to segment JK. That perpendicular means intersecting at a 90-degree angle, and it is extremely important in terms of the special property that this line will have. We also have the markings that indicate there that JR is congruent to RK because they're each marked with one mark. Which means that R is the midpoint of segment JK, indicating that RS is in fact bisecting JK because it's passing through the midpoint. This allows us to use perpendicular bisector in a sentence here, saying that line RS is the perpendicular bisector of segment JK. And it's worth noting that only line segments have bisectors because in order to be bisected you have to have a finite length. And if it's a line, it has infinite length. So you can't cut something that's infinitely long in half. So instead we only have these when it comes to line segments. That's why they come up in triangles, because triangles are made up of three line segments. So here we have an example. RS is the perpendicular bisector of JK. Now perpendicular bisectors have a special property. That special property is going to come to us in the form of the perpendicular bisector theorem. Now that theorem reads, if a point is on the perpendicular bisector of a line segment, then it is equidistant from the endpoints of the segment. So in this picture, we have CD clearly indicated as being the perpendicular bisector of AB. Again, it has that perpendicular mark, boxy, indicating that there's a 90-degree angle between line CD and segment AB. And we have the congruence markings indicating that AD and DB are congruent, meaning that D is the midpoint and CD is bisecting. What that tells us is that every single point on CD, every point on this line, has a property. So point C is one of those points. C is the same distance from A as it is from B, meaning that AC and BC are equal or congruent. As it turns out, the converse of that statement is also true, leading to the converse being presented below. If a point is equidistant from the endpoints of a line segment, then that point must lie on the perpendicular bisector of the segment. So if we look at this picture, since E is lying on line CD and EA is equal to EB, that is enough for us to state that CD must be the perpendicular bisector of AB. So we're going to use this in a few examples. What I would suggest is that you pause the video and try the first two examples on your own. And then resume the video and see if you kind of have figured out the idea on your own or if you need a little bit more explanation. Thank you for your pause. Okay, so here we have two problems dealing with perpendicular bisectors. And these are both relatively simple problems. In theory, you may actually talk yourself into being worried about whether or not these are trick questions because they generally are that simple. Okay? Here in the picture, we have clearly indicated that AC is the perpendicular bisector of segment BD. How do we know? Well, we've got the perpendicular marking in the form of the right angle, and we have the congruence markings indicating that C is the midpoint. This immediately tells us that AD must be congruent to AB by the perpendicular bisector theorem from the previous slide. Which means, by the definition of congruence, AD is equal to AB, meaning that AB is 4.1 units. Okay, so don't overthink these problems. Don't worry about whether or not they're trick questions because in general they are relatively simple questions to solve. So number 2 asks us to find the length of RT, which is a little bit harder this time. Same exact reasoning though. We can state that QR and RT are congruent because of the perpendicular bisector theorem. Okay, we clearly have it marked that RS is perpendicular to QT, see the right angle, and QS and ST are equal, meaning S is the midpoint. That means that RS is the perpendicular bisector of QT, and it means that R is equidistant from Q and T. Now, what that allows us to do is set up an equation to solve for x. 2x plus 3 equals 4x minus 7. We can solve that equation by moving the x to one side and the number to the other, giving us the equation 10 equals 2x. Then we can divide by 2, which gives us x equals 5. Now that's great, but that does not answer the question. We were asked to find the length of RT. So RT, what we're going to do is plug x in, plug 5 in for x. RT is listed as 4x minus 7, so that would be 4 times 5 minus 7, or 20 minus 7, which is 13, meaning that RT has a length of 13 units. There are 3 more of these on the next page. I suggest that you pause the video, try them on your own, and then resume the video to see how you did. Okay, so here on number 1, we've got some distractors. Now I will point out that we're using the same picture for both of these problems. So what I'm going to do is I'm actually going to recreate this picture and then shrink it way down so that it fits, and I'm going to actually basically use a new copy of that for each part of the problem. Okay? So on the first problem it says if Wx is 25.3 units and YZ is 22.4 units, and WZ is 25.3 units. Find XY. Well, the markings, we don't even really need the 25.3s with the way that the picture is marked. But in theory, what they're searching for here is they're trying to see if you recognize the converse of the perpendicular bisector theorem. If WX is congruent to WZ, which it is because they're both 25.3, that means M must be the perpendicular bisector. And that in itself is enough for us to state that XY is congruent to YZ. Now it's also enough that they're both marked. Okay, they're both marked. So XY must equal YZ, which means that XY, which is what we're trying to find, is 22.4 units. Okay, again, it's a relatively simple question. Please don't confuse yourself into thinking it's harder than it is. On number 2, M is the perpendicular bisector of XZ, and WZ is equal to 14.9. They ask us to find WX. Well, WX must equal WZ. They must be congruent according to the perpendicular bisector theorem, which means that WX is equal to WZ, and WX is also 14.9 units. Okay, don't overthink it. Don't overthink it. Relatively simple idea. So on the third question, same picture. If M is the perpendicular bisector of XZ, WX is 4A minus 15 units, and WZ is A plus 12 units. They ask us to find WX. So this is going to be a two-step process. First, we need to find the value of A. Well, the perpendicular bisector theorem says that WX must be congruent to WZ. It's a little bit sloppy, so let me clean that up real quick. There we go. Which means that WX is equal to WZ, meaning that 4A minus 15 has to equal A plus 12. We solve that equation for A, so we subtract A from each side and add 15 to each side, which would move the A to the left and the number to the right. That would give us 3A equals 27, and then we would divide each side by 3, which would give us that A is 9. Now, notice I didn't write 9 units because we don't know what A is. A doesn't necessarily have units, okay? And A is actually not the answer to the question anyway, so, we're just going to move on. We need to find the length of WX. So since WX is equal to 4A minus 15, we are going to plug 9 in for A, which would give us 36 minus 15, meaning that WX is 21 units. Okay, so that does it for perpendicular bisectors as their own idea. That's going to be the end of the first video. Our next video is going to introduce a new vocabulary word and apply it to the perpendicular bisectors of a triangle. And then our third and final video for this section will cover angle bisectors in triangles. Thank you very much for your time and attention.